All right. Okay. Well, yes. Happy Friday, and hope you are all staying safe and cozy and warm in the rain. And thanks for making it to class. Today we'll continue our lecture on numeric methods, and so we left off on Wednesday. On Wednesday, we introduced some root finding methods, and we got through. What did we get through? We got through fixed point iteration, and then Newton-Raphson method, secant method, and then and today we'll look at bisection method. So bisection method is another root finding method where we're trying to find where the function is equal to 0. And a great thing about bisection method is that it's almost always going to work. All right, it's just the only requirement is that the function is continuous. And if the function is continuous and you have a bracket where you know a root exists, then bisection method will find the root. The only kind of disadvantage is that its convergence is kind of slow, linear convergence. But other than that, I mean, a lot of these things, they work pretty quickly. So, yes, your computers will be able to converge fairly quickly. So, anyway, let's go ahead and take a look how bisection method works. So basically, we start off. We begin and say there's some kind of continuous function, and we have some kind of interval, an interval that goes from x on the left to x on the right, so which I've called xl and xr. Okay, so you have some interval. The two endpoints of the interval are xl and xr, and if one of those are positive and the other is negative, okay, and the function's continuous, then that means the function has to cross basically the x-axis, and that therefore there must be a root somewhere inside that interval. So either the value on the left side is negative and the value on the right side is positive, or the value on the left side is positive and the value on the right side is negative, and that means there has to be a root somewhere in there. Okay, and so kind of a quick way to check is you can just say, hey, is the product of the function on the left and the function on the right, is that product negative? And if that product is negative, then there must these things will have opposite signs, and there must be a root somewhere in between the left side and the right side. Okay, and so we take that interval, and what we do is we basically keep shrinking that interval in half, and we keep going until the width of the interval is less than some value epsilon. Okay, so we keep going until the difference between x on the left and x on the right is less than some arbitrary value, like 10 to the negative 6 or 10 to the negative 8, whatever you want. And then we say, okay, well, that's close enough, and we'll stop there. So this is the algorithm as described. Well, first of all, so you'll check if the difference between the right side and the left side, if that value is less than epsilon, then we'll go ahead and stop. Okay, and if it's greater than epsilon, then we want to keep shrinking the interval until it is. And so we'll compute the midpoint, which is going to be xm. The midpoint is just the left side plus the right side divided by 2. Okay, and if that midpoint happens to be equal to 0, then we'll go ahead and stop. So because then we found the root. Otherwise, we will compute what is the product of f on the left and f at the midpoint. Okay, and if that value is negative, then that means the left and the midpoint have opposite signs, and the root has to be between the left and the midpoint. And if that's the case, then the midpoint will become our new right bound. And so we will assign xr to be equal to xm. Okay. If that quantity, f on the left and f at the midpoint, is not equal to 0, is not less than 0, meaning f on the left and f at the midpoint have the same sign, then the root must lie in between the midpoint and the right-hand side. Okay, so if the root lies in between the midpoint and the right-hand side, then what we'll do is we will assign the left-hand side of the interval to be the midpoint. Okay, so we will do that. So this is this is really the one kind of the critical step of the bisection method, and then we repeat, and then we repeat. Okay. So notice that at every iteration, the left side and the right side, there's always a root in between there, and we just kind of keep going. So we start with the assumption that there is a root, and we have our error at every turn. Okay. So here's an example. We'll take a look at the same function that we looked at on Wednesday. So we've got f of x is log of x minus e to the negative x. Okay, f of x being log of x minus e to the negative x. And so here's just my function. I'm going to just start off with the interval 1 and 2. And we'll say our tolerance, we're going to stop when we drop at 10 to the minus 8. And we're going to calculate the function at x on the left, and I'll call this FL. The function at x on the right will be FR. And when we do that, do the left side and the right side have opposite signs? FL times FR, is that less than 0? That is true. So that means there is a root somewhere in there. And this is the bisection method code written up. So I'll start off with 0 iterations, and if the right side minus the left side is greater than is less than the tolerance, we will kick out of our while loop. Otherwise, this loop will just keep repeating. Okay, we're going to calculate the midpoint, XL plus XR over 2, that's the midpoint. We're going to calculate the function at the midpoint. Okay, and then we're going to ask, is the function of the midpoint equal to 0? Now I wrote this funny little thing, all equal fm comma 0, and is that identical to true? This is kind of like saying if all equal is equal to true. So a lot of times if you just have a logical vector or logical value, you don't have to do equals true. So sometimes I see this in your homework submissions. It'll be like if verbose equals true, all right? That is unnecessary. You can just do if verbose, all right? So because verbose is either going to be true or false, so you can say if verbose, then execute this code, and if verbose, verbose is going to be true or false, and if verbose ends up being false, then it won't execute the code, right? So you don't actually have to do if verbose equals true. That's a little bit of a silly thing. But unfortunately, this all equal function, I don't know if you've used it, but all equal. So remember, with with floating point numbers, okay? With floating point numbers, you don't actually, for something to be equal to 0, it has to be exactly equal to 0. And so values that are close to 0 but not really exactly 0 will end up, if you do equals, will be false. So we're going to do all equal being approximately equal is f at the midpoint approximately equal to 0. And unfortunately, this function returns either true or a text string that says like relative error point, whatever, okay? And so here I'm basically saying is all equal, approximately equal to true or something else, and that's what the identical, is it identical to true, yes or no? So this is going to be if the midpoint is approximately 0, we will break out of the loop. Otherwise, we'll keep going. Okay, so that's what this is. This line is just saying, hey, is f at the midpoint approximately 0 or not? Okay, now we do the check. If the product of the left side and the midpoint is less than 0, that means the root lies between the left side and the midpoint, and then we will take the midpoint and make that the new right side of the interval. Okay. Otherwise, that means the root lies in between the midpoint and the right side, and the midpoint will become our new left side. And so this is the bisection method, and then I'm going to increment my number of iterations to add 1 to that. Okay. When the loop is all done running, I will take the average of the left side and the right side, the midpoint of the left and right side, and that will be my root. So my approximate root is 1.3098. How many iterations? It took us 24 iterations to get to this, okay? So if you recall Wednesday's lecture, I think it took about 19 iterations for fixed point iteration. It took about 4 or 5 iterations for Newton-Raphson method. So this one takes a few more iterations, but again, it runs very quickly anyway. But yes, it does take more iterations. Here's an illustration of how the bisection algorithm works. So we have our starting endpoints of the interval being 1, x equal to 1, and x equal to 2. And we can see this side is negative, this side is positive. And so there is a root somewhere between 1 and 2. We calculate the midpoint at 1.5. And the midpoint is positive. And so the left and the midpoint, the root will be between the left and the midpoint. So we can eliminate all of this. We can eliminate half of our interval. Okay, I'm going to calculate another midpoint, which will be at 1.25. And this midpoint at 1.25, the function is negative, and therefore the root lies in between 1.25 and 1.5. And so we keep this, so our interval is half of that. We take the midpoint there, and we'll eliminate that side. We'll take the midpoint, and this is very close, okay? Very close to the root, but it's not, and so we get, we will keep this side. This is negative, and this side is just a little bit positive. And we keep running, and we can see that our interval keeps getting smaller and smaller and smaller. All right, and so this will just keep running over and over and over until the width of the interval shrinks to be less than that tolerance, and that's when it kicks out. Okay, so that was, what is this? 1, 2, 3, 4, 5, 6 iterations, and if you go to 24 iterations, the difference between the left and the right side will be, less than whatever our tolerance is, which was, I think, 10 to the minus 8. So pretty small, okay? And that's bisection method. So that, and this is guaranteed to converge on any kind of continuous function. So as long as you have a continuous function and you have a starting interval where there is a root somewhere in that starting interval, then this will find it, okay? So, the disadvantage of bisection method is that its convergence is a little bit slower, and so there is kind of this best of both worlds approach, which is we start off with kind of this root bracketing bisection method, which is safe, and then we keep running until we get close enough. All right. Close enough is when the function is approximately linear, and at that point we will switch over to Newton-Raphson method, and that will speed up the last few iterations. Okay, so I guess at some point maybe around here or whatever, we could say, all right, let's switch over to Newton-Raphson method. This looks kind of like a linear function at this point, and then Newton-Raphson method will find roots very quickly when it's approximately linear. Okay, let me go ahead and give you your first view quiz answer. Today's first view quiz answer is the letter D. D as in dog. D as in dog. So we'll talk a little bit about orders of convergence, and just kind of how quickly some of these algorithms converge to a solution, and the idea is, okay, well, how big is our error, right? Our error is the difference between the actual value of the root and our approximation of the root. Okay, so we have the root is a, our approximation is xn at time n, and the error is epsilon sub n, right? So the error at time n is epsilon sub n. And then we think about, okay, how does the next value, okay, epsilon at time n plus 1, how does that compare to epsilon at time n? How much smaller is the next amount of error? So the idea is, we want the next amount of error to be smaller than our current amount of error at time n. So if we can raise our current value to some power p, multiplied by some constant, okay, this means the next value of error is some degree, some order of convergence. I mean some degree smaller, some order smaller than the previous value, and larger values of p correspond to faster convergence. Okay, if you are interested in kind of some of the derivations for the orders of convergence, you can read these notes here. But this is kind of what we have. And so what we'll, starting off with kind of bisection method, if you think about, okay, what is the size of the amount of error in the at the next iteration for bisection method? Well, the amount of error in the next iteration is half of our current amount of error, all right? And so so we would just take our error and then it's raised to the 1 power, right? So our p is 1. And so our order of convergence is 1. That is considered linear convergence. So it's not very, very rapid, but it works, okay? And I wrote, it can be shown that. So again, you'll have to kind of consult the notes if you're interested in seeing the actual order of convergence for Newton-Raphson method. But under certain conditions, kind of when it is approximately linear and things like that, the Newton-Raphson method will have a order of convergence of 2. That the next at the next iteration, the amount of error is kind of your current amount of error, raised to the 2nd power. So we call that quadratic convergence. The secant method has an order of convergence of 1.6, around 1.6, which is the golden ratio. Each of these things have their kind of advantages and disadvantages. Newton-Raphson method, you have to find the derivative, and it has to behave well, and then it will converge rapidly. Whereas bisection method, this one is guaranteed to converge, but it converges a little bit slower. So, what do we do? There's some trade-offs there. Okay, let's talk for a moment about derivative approximation. And so, if you think about some of these methods, like Newton-Raphson method required that we have the derivative of the function at some point x at time n, right? So we say, at the next time interval, next iteration, x at time n plus 1, we take our current value xn minus the function at xn divided by f prime of xn, right? So this is to kind of find, the length of the run. We did the rise divided by the slope, but this requires us to figure out what that slope is, what that derivative is. Okay, and so so a lot of times what we'll do is, when implementing our algorithm, we'll write a function for the function, computer function, and we'll write another function for calculating the derivative. And so here's a simple example. This is the same function that we've been looking at. Our function is log of x minus e to the negative x, and we said, what is the derivative of this function? The derivative of this function is 1 over x plus e to the negative x. F prime is 1 over x plus e to the negative x. And then we implement this by just writing up our function. We have f is function of x, log of x minus e to the negative x. And f prime is a function of x, and it's going to return 1 over x plus e to the negative x. And then so I can plug in, what is the function at 5? And it's 1.6027. What's the derivative at 5? F prime at 5 is 0.2067379. Okay? And so this function is simple enough. All right, so here's a picture of the function at 5 and the tangent line at 5. Okay? That function is simple enough where we were able to find the derivative, and it was pretty straightforward, okay? And I would say in our class, most of our functions will be fairly straightforward, not too hard to find some of these derivatives. But you could also imagine you might run into a situation where figuring out the derivative, using calculus and using some kind of analytic method to find the derivative, ends up being tricky or ends up being hard to do. And in that case, it is helpful to have a numeric way to approximate the derivative. Okay, and this is it's not also just helpful in cases where it's difficult or sometimes you just want to double check your answer. Right? So let's say you have this complicated function and you say, all right, this is the derivative of this function, and you want to kind of double check your answer and just say, like, did I do this correctly? If you can approximate the derivative numerically, then you can kind of compare this, right? And so here we're going to try to calculate and end up at the same answer without actually doing any calculus here. Okay, so this we're going to kind of think back to what is the definition of a derivative in calculus, right? And so one of the definitions for the derivative in calculus is this. We said, okay, the derivative f prime at location A is, think of A and think of some small quantity h, okay? You add h to A and you calculate the function there. You subtract off f of A, right? So how much did the function change when you added h to some quantity A? And you divide by h, right? And you take the limit as h goes to 0. So as that little kind of little delta, as that little distance gets smaller and smaller and smaller as it gets closer to 0, that's going to be the definition of the derivative. Okay, and so we're going to just basically use this thing, and we're just going to say, okay, well, we'll not use h equal to 0, but we'll set h to be some small value, like 10 to the minus 5 or 10 to the minus 6, and we'll see, we'll approximate the derivative like this. So here is, here's our function, log of x minus e to the negative x, and I'm going to say, all right, plug in some value x, all right, and my h is going to be 10 to the minus 6. And so what I'm going to do is I'm going to calculate the value of the function at x, and then I'm going to do x plus h and calculate the value of the function at x plus h. So I have log of x plus h minus e to the negative x plus h. And then I say, all right, well, what's the difference between f of x h and f of x? Take that difference and divide by h, and that will be an approximation to the derivative, okay? So here I'll plug in h equal to 10 to the negative 6, and I have to say how many digits we want, because otherwise it's going to look like it's the same, right? So this is what I get when I use this approximation, right? So I'm going to do f prime approximate value for x equal to 5, and I get 0.2067379236669. Okay, compare that to the true, quote-unquote, true value, and I put true in quotes because it's everything on your computer is an approximation because we're using floating point numbers. So, you know, f prime of 5 is just using 1 over x plus e to the negative x. So we're using kind of the definition from calculus, or the value of the thing, and we get 0.20673794699. Right, so we are accurate up to 7 places behind the decimal, okay, 2067379, and it's only until we get to the 8th place that we are off. So this ends up being 23699, and here we end up at 46999. Okay, so in my opinion, that's pretty good. It's pretty good. Okay. Here I did x plus h. H is this positive quantity, 10 to the minus 6, and you know, in calculus, you know, you learned about like discontinuities and stuff and your derivatives, and you probably learned about like, okay, what is the derivative when you approach h, when you approach 0 from the right hand side? What's the derivative when you approach 0 from the left hand side? Okay, so what if I take the left hand side derivative? And so here I'm going to do h is negative 10 to the minus 6, okay? And I'm going to use the same definition. So I'm going to do f of x and f of x plus h, but this time h is a negative value. So I'm going to have like 5 and 4.999. What's the difference? Divide by h. And if I do that, I get a value very close, but a little bit off, okay? So if you look at this, all of these are accurate up to around 7 places after the decimal, but let's look at these last kind of few digits here. So the left-hand side derivative approximation is a little bit too big, okay? All right, it goes 737970299, okay? And the right-hand side approximation is a little bit too small, 737923669, okay? Versus the actual value is 73794,699, okay? So we're ending up at 7 versus 2, and the actual value is around 4. And that's because there's a little bit of curvature in the function, and we have it's concave down at this point. And so here's a exaggerated illustration, okay, So the function is this blue line, okay? And the true tangent line is this dotted red line, okay? True tangent line is this dotted red line. And so, what's going on here is the left side derivative, okay, is, here we're at 5. And if I draw the left-hand side approximation, exaggerated, we can see is like it crosses here and here, and so this slope is a little bit too steep. The right-hand side derivative, okay, it crosses at 5, and then we use the right-hand side, h is some positive value, and so its slope is a little bit too shallow, okay? And so what we can do is that we can say, all right, let's take the average of the left-hand side and the right-hand side, okay? And so to take the take the average of these things, I'm going to have h, kind of my balanced approximation, is I'm going to have h is 10 to the minus 6 again, and then so I'm going to have f of x plus h and f of x minus h. So I'm going to do log of x plus h, and then log of x minus h, and we'll do, what's the difference there? And we're going to divide by 2h there. All right. Does that kind of make sense as far as what we're doing here? All right, and so when we do that, my approximation to the derivative is 0.20673794694, and so now we are accurate to 10 places after the decimal, okay? 20673799469, and it's only these last two digits, 84 and 99. So we're off just by a tiny, tiny, tiny bit by using this kind of balanced derivative approximation. And that's going to be, this is about as accurate as you can get. So without, considering floating point numbers, and so that's pretty good. So this is a way for us to approximate derivatives without actually having to do any kind of calculus and actually finding out the derivative. Okay, we're taking, again, all of these numeric methods that we're doing is saying, hey, what is the computer good at? The computer is good at crunching numbers, okay? All right, it's not good at doing like finding derivatives and stuff. Again, Wolfram Alpha, incredible software, it can actually figure out derivatives. But in general, computers aren't really designed for that. It's really good at just crunching numbers. So we just say, all right, here's a number. All right, calculate this thing for 5.0001, and what's the number I get? Calculate this thing for 4.999. Okay, and what do I get? And we say, okay, now we can approximate a derivative there. Okay, we can generalize this thing. So all of these functions I've been doing log of x plus h and exp of this thing. But what if I just want some generic function? Well, here, with R, arguments for a function can be other functions themselves. Okay. And so you've seen like the apply function, right? Apply, you put in you provide another function and applies that function to the thing. So here we're going to write a function where one of the arguments is some arbitrary function ftn, okay? And so we will take x, and then we'll have a default value of h to be 10 to the minus 6, and we'll do left side will be x minus h, the right side will be x plus h, and then we will calculate using the function that we've provided, calculate the value of the function on the right side, calculate the value of the function on the left side, divide by 2h, okay? And so we can plug in any arbitrary function, and this thing will approximate a derivative, okay, at some arbitrary location x, okay? And so so this is kind of a neat thing. You're going to have a function that calculates the derivative. Now, we won't have a symbolic representation of the derivative, but all we'll say is like, okay, you plug in a value, and this function is going to spit out another value, and that value is going to be approximately equal to the derivative. So here, the original thing, if my f is log of x minus e to the negative x, I can plug in find f derivative of f at 5, and it gives us our value, 0.20673799469. Okay, here's another function. Here, if I just say, my function, I want to use x squared, okay? What's the derivative of x squared? That's going to be 2x. That's very simple. But I can just say, all right, give me the derivative, f derivative of x squared at 5, and it says, oh, that answer is 10. So that's pretty good, okay? Now, we can see if I say print out 12 digits after the decimal, we see it's not exactly equal to 10. It's 10.00000000014. So it's pretty, that's what, 8 places after the decimal, 9 tenths. So I guess it only prints out 10 places after the decimal. I don't know. I guess with 10, it's, I don't know, significant up to there. So it's we have 10 significant figures of accuracy. Okay, so pretty good, Okay, and that's what we have now. Here, wait, okay. Let me give you your next view quiz answer. Second view quiz answer today is E. E as in elephant. E as in elephant. We look at this thing and we say, okay, what am I adding? What is my what is this little h that I'm adding? And I'm adding 10 to the minus 6. Okay, and you might look at the definition of the derivative and say, well, it's the limit as h goes to 0. And so there might be a temptation to say, hey, let's add the smallest h we can add. Okay, that if I keep shrinking my h, we've got to get more and more accurate values. Okay, there's a temptation to do something like that. And I bring this up because that's not always the, it's not going to work that way, all right? Because you're using floating point numbers. And so, yes, in real numbers, the definition of the derivative is as h goes to 0, okay? But with floating point numbers, you might actually get more accurate results by using a larger h than a smaller h, okay? And that's because, my hope was, with the time we spent last week on floating point numbers, we realized that there are limits to how much information we can store. And, as your numbers get bigger, what's the smallest thing that you can add? The smallest thing that you can add also has to grow with the numbers that you are adding, right? So, when you have 1, the number 1, you can add 2 to the negative 52, okay? But if you have a number like 100, then you can't add 2 to the negative 52. It's got to be like 2 to the negative, 2 to the negative like 40 something, okay? So it ends up being a lot, you can't add as small numbers. And similarly, when we're doing kind of derivative calculations, we're going to end up with some numbers, and we can't do h plus some tiny value, right? So I wanted to just show you how our accuracy actually gets thrown off by using smaller and smaller h's, okay? So if I use like 10 to the minus 5, my accuracy, I'm accurate, so I've got 9.9999999, okay, 6. So I'm off by, in the last 6 digits, I'm off by some quantity there, so around 38.8. And then when I add 10 to the minus 6, my amount of error is less, 139, okay, in the last 6 digits. But then if I add 10 to the minus 7, the amount of error that I have is actually more, okay? This is more different from 10, right? The true value is 10, and when I'm adding 10 to the minus 7, how different is it from 10? It's actually even greater than this, okay? What if I do h is 10 to the minus 8, okay? The amount of error is actually bigger here than it was when I did 10 to the minus 5, okay? And as my numbers get smaller and smaller, 10 to the minus 10, 10 to the minus 12, 10 to the minus 14, at 10 to the minus 14, the true value is 10, but my approximation is pretty far off, 9.77 basically, okay? And if I try doing 10 to the minus 15, my derivative approximation is, I would say, is very far off at 8.88, the true value being 10. And if I try to do 10 to the minus 16, my derivative ends up being 0, okay? So 2 to the negative 52 is around 10 to the minus 16. And basically at this point, if my value is 5 plus this, the computer's not able to render that or understand that, right? 5 plus this is the same as 5 to the computer. It cannot distinguish between 5 plus this quantity versus 5 by itself, okay? it is able to distinguish between 5 plus 10 to the minus 15, but not very well. All right, so our accuracy actually, goes down as we try to use smaller and smaller h's. So yeah, in real numbers, the derivative is when h goes to 0, okay, in real numbers. But we don't have real numbers, we have floating point numbers, and we actually get more precise answers. Our answers are more accurate by using a larger h, okay? There's no one-size-fits-all answer, all right? Again, it depends on where you are in the number line and how far apart the values are spaced out there. So when so here we're trying to find the derivative when x equals to 5. But if you're trying to find the derivative where x is equal to 5,000, you probably might not even be able to add 10 to the, you can add 10 to the minus 6, but you're going to have to, you'll probably get more accurate answers by doing plus or minus, 0.1, okay, rather than 10 to the minus 1 rather than 10 to the minus 6 or something, okay? So when h gets really small, the accuracy drops dramatically, and then when h is too small, it can't even calculate a derivative approximation. So these are things to keep in mind. This is kind of part of why we spent a lot of time discussing floating point numbers, is because when you're dealing with numeric methods, sometimes there's a temptation to treat them like real numbers and say, all right, if I keep doing this thing and shrinking the amount of, the increment that I have, I might get more accurate results, and that's just not the case. That's not the case. Okay, so if we have a way to find derivatives, okay, whether we can find derivatives analytically using calculus or just approximate derivatives using one of our derivative, our numeric method for approximating derivatives, we can now start to do some numeric optimization, okay? So even if you don't, even if you only have the function that's able to approximate derivatives, you can still use these methods here, because you just treat the function as just like a little black box machine. You put a value in, and it spits a value out. That's really all functions do. It takes a value in, does something, and it spits another value out. And so we have this derivative function that says you put a number in, and here's the value that comes out that's approximately equal to the derivative. So, we started off with root finding methods, find out where the function is equal to 0, and we can use them to find local mins and local maximum, local minimum and local maximum. Okay, a lot of our algorithms that we're going to look at for optimization is for finding local minimums. If you want to find a local maximum, you just take the function, multiply it by -1, and you say, all right, what's the minimum of negative f is going to be equal to finding a max of f of x, okay? And how does derivative-based numeric optimization work? Well, it's basically what you learned early on in like Calc 1, where you find the derivative and you say, okay, where do we want to find a local min or local max? Find the derivative of the function, set the derivative equal to 0, and you solve. So when the derivative is equal to 0, that will be a critical value that will either correspond to a local min, local max, or like a saddle point, right? So, so that's what we have. Okay, so we're going to try to find locations where the derivative is equal to 0. So we just find the derivative of f, either analytically using calculus, or we use the derivative approximation, and then we're going to apply any of the root finding algorithms to find where f prime of x is equal to 0, okay? And then we evaluate the critical points. And so here we can try using Newton-Raphson method. So for Newton-Raphson method, rather than finding the roots of f, we're going to find the roots of f prime, okay? And if we can find the roots of f prime using Newton-Raphson method, well, those will be the critical values, and those will correspond to local mins or local max. So so for Newton-Raphson, to find roots, you take x sub n minus f divided by f prime. This time my f is f prime itself, so we're going to do x sub n minus f prime divided by f double prime. Okay, and so this will give us the next value to use at our next iteration, and we just repeat this until the derivative f prime of x is close enough to 0. It's less than some epsilon. So conditions here is that the function needs to be twice differentiable. And then f double prime, this thing cannot be 0 for any of the x's that we check. Okay, it is allowed to be 0. You are allowed to have inflection points and things like that, but it just cannot be one of the values in your sequence of x of n values, right? And so if it ends up being in your sequence and it breaks, just try a different starting point, and maybe you'll have better luck there. Okay, or it could just be one of those cases where Newton-Raphson method doesn't converge, right? So that those are things that happen with Newton-Raphson method. Sometimes it doesn't converge. All right, so let's just take a look at a simple example here. So here's my function, 0.25x to the fourth minus 0.5x squared. This is a simple polynomial, so we are able to find f prime and f double prime very easily. But even if you couldn't, you could use just kind of the numeric approximation for derivative, and that would be good enough here, okay? So the derivative is x cubed minus x, and the second derivative is 3x squared minus 1. And so we will code all of this up, okay? And we're going to just say, let's find the roots of f prime of x, okay? And that will be the critical values or critical points. And so here's my function, 0.25x to the fourth minus 0.5x squared, and we can see, all right, we'll have a local min at -1, a local max at 0, and a local min at +1. And let's see if our function is able to identify these local mins and local maxes, okay? So my f prime is x cubed minus x, my f double prime is 3x squared minus 1, and I'm just gonna apply Newton-Raphson method. So I'm going to start off at 2.1, and we'll say the next iteration will be x old minus f prime of x old divided by f double prime of x old, right? So I'm just using this exact thing, okay? And we'll run the while loop. We'll say as long as that difference is greater than some tolerance, we'll keep running the iterations, and with the next iteration x new being x old minus f prime of x old, f double prime, okay? And so anyway, if I start off at 2.1, it converges to, it says, here's your solution. You will have a critical value at 1, and indeed 1, it corresponds to a local minimum, okay? Let's try a different starting location. So instead of starting at 2.1, what if I start at 0.9? Okay, starting at 0.9, I end up finding a critical value at 1.0003, so pretty much 1, okay? And so that will also be one of the solutions, okay? And so all of this really kind of just depends on where our starting location is, right? So a lot of Newton-Raphson, which root does it converge to depends on where your starting location is. So if I start off at 0.1, then I end up at a value very close to 0, 9.9 times 10 to the negative 24, okay? So for all intents and purposes, that's 0. So for floating point numbers, anything less than like 10 to the minus 15 or something is pretty much 0, okay? So we get 0 here, and then if I start off at negative 10, it says there's a local min, or it says there's a critical value, critical point at -1. So either local min or local max. And from our picture, we know it's going to be a local min. Or yeah, local min at 10 to the at -1 here. Okay, so these are just a couple examples of this, and again, it will apply to any kind of, you can apply any root finding method, not just Newton-Raphson, but Newton-Raphson is one of the more popular root finding methods that we have here. Okay, I gave you 2 view quiz answers. Okay, third view quiz answer is A as in apple. A as in apple is your third view quiz answer. As an apple. All right, we'll end a couple minutes early today. So have a great rest of your day. Stay safe and warm despite the weather, and we will see you all on Monday.